thank you all for coming. My name's Zach. If this wasn't a spoiler and the sign up on the website wasn't a spoiler, this is an introduction to property-based testing. So if you thought you were doing a different tutorial, now is a good time to run away screaming. Otherwise, let's jump into it. We've got about 4 hours together, and conveniently, I'm going to break this into 4 sections. So each one consists of me giving a short talk, followed by all of you doing a bunch of exercises while I wander around and try to debug everyone's differently broken Python setups. Or maybe the actual content once we get into the second section. So the basic plan is that first I'll start by telling you what the heck property-based testing even is, because I am serious about introducing it. And then we'll talk about a couple of specific things. The first one, how we describe the input data for our tests. Then we'll talk about some common tactics you can use. And then the last section is one that I think is often missing from introductions, but it's designed to be like some of the practical stuff that you'll run into when you like get back to your real project. You're like, okay, how do I apply this when it's not a tutorial? Like, what are the configuration options that I might care about? What are the performance considerations? That kind of thing. So, property-based testing 101. Let me just start with like some quick shows of hands. Who here has written unit tests? That's good, because that's pretty much assumed knowledge. Who here has used PyTest? PyTest, yeah. Anyone prefer unit test? That's fine. Like, you can use it with either. But I think you're probably right to prefer PyTest. Who here has used PyTest parameterize, like the @mark PyTest parameterize decorator? Okay, most of you. I'm just going to start by defining testing in the first place. So the definition that I'm going to be using is that testing is sort of the art and the science of running your code and checking that it did the right thing. And often that's infeasible, so mostly we just check that it didn't do the wrong thing, or didn't do some specific wrong things. Like, it's much easier to check that your code didn't crash than that it got exactly the right output. And sometimes that's all you need. There are a lot of cool things you can do to kind of improve your productivity or improve your code quality that are not testing. I think many of these things are good, but I'm not going to be talking about them in this because they're not testing. You know, you can use assertions in your code, not just your tests. You can use type checkers, linters, get a colleague to review your code. You can have coffee and or sleep, on good days both. And then there are a whole bunch of different kinds of tests you might find yourself writing. You can have unit tests or integration tests. As far as I can tell, these are distinguished by people arguing about names on the internet. There's no actual meaningful distinction. They're just like, a unit test is small-ish relative to my integration tests, while my integration tests are large-ish relative to my unit tests. It's a fuzzy boundary even for within one project. But the others are like a little better defined. So snapshot tests are where you run one version of your code on a known input and you save the input and the output, and then later when you've changed your code, you run it again and check that you got the same output. This can be really valuable where it's hard to define exactly what your code should do, but you can say like, well, I didn't expect that change I just made to make a difference to the output. And then sometimes you make a change that you do expect to make a change to the output, and you're just like, yeah, it's fine, commit the new output. This is still a really valuable, quite easy technique. You can have parameterized tests. So I just checked in about these earlier. Most people have used them. You have a decorator, you sort of write down a list or a table of the possible inputs and maybe outputs that you expect from your test. You can have fuzz tests. This is another style that's related. You sort of throw random or other arbitrary inputs to your function and see if it crashes. Or you can have property-based tests, and that's what we're going to be talking about today. My friend David is driven to drink by bad examples in tutorials. So with apologies to David, we're not going to use that bad example of reversing a list. Instead, we're going to test sorting a list. Has anyone here ever sorted a list? Or an array? Yeah, most of us. No? Well, what you do is you take an input list or sequence of comparable things, and you output a list of those things such that each one is not less than the previous element. And so this is a set of unit tests for a sorting function. We check that 1, 2, 3 gives us 1, 2, 3, that 3, 2, 1 gives us 1, 2, 3 still as floats, and that you can also sort strings. It's not just numeric. Okay, and you can parameterize this by just having a table of the input and output values. And so this is particularly nice because it makes it easier to add more test cases. If someone reports a bug, it's much easier just to pop a new entry in than to write a whole new test function. And it makes it clear that all of these inputs and outputs are testing semantically the same thing. And sometimes we might actually have like a trusted function that does this thing. Maybe it's software that someone wrote previously. Maybe it's my fancy multi-threaded code running on a single thread instead of many threads. But sometimes you can just compare your implementation to a known or assumed correct implementation. And that's quite a powerful technique as well. It saves you having to work out by hand what the output should be. But sometimes you don't have that. And this is where we start to talk about the properties in property-based testing. You could think of them as invariants, things that should always be true of your code. And so in the case of sorting, we can just say that, well, if you like zip the list together with the list shifted, then you should have this comparison relationship between every element. Does this seem like a reasonable test to people so far? I'm getting some vague nods. Okay, how could it not catch a bug? Like, could we have a buggy sort function where this test passed, but the function was really, really, really bad? What would that be? Return empty list is not caught by this function, because the empty list is indeed sorted. It's not the input sorted, but it is a sorted list. Okay, so we'll check that we have the same number of elements and the same set of elements in the input and the output. Just like shout it out. Who could write an evil implementation that makes this test pass without being a correct sorting function? Anyone?
You could replace the contents with...
Yeah. If you have duplicate elements...
Sorted list of the same length.
Yeah, you can. If you have duplicated elements, you can like sort the set, and then just append the last element however many times. So if you input, for example, 1, 1, 2, you could output 1, 2, 2. So, okay, the mathematical definition is that sorting is a permutation of the input such that the ordering holds. The only problem here is that iterating through every possible permutation of a non-trivial list is going to take a really long time. Even though this is pretty much correct, it's going to be too slow. So we can turn to the collections.counter class, like count each unique element and assert that we have the same number of each element in both sides. Is this test good? Well, it is a property-based test, right? The two properties we're checking is that the result is sorted and that the result is a permutation of the input. We can't always do a complete specification of our function. For example, we might often have something where we can say, look, there are certain conservation laws in my simulation, right? I should conserve mass, matter, energy, momentum, whatever else it is, without being able to specify exactly what the output should be, other than by just running my simulation. I was part of a COVID modeling project at one point where it turned out the things we failed to conserve included the number of people in the simulation. And it's kind of embarrassing if your epidemiological simulation just like vanishes people who are sick because it's inconvenient to track them. So a little bit of testing can still be a very powerful thing. But as it happens, you can upgrade it with hypothesis, right? And so hypothesis gives you like basically three things. The first is this @given decorator. @given is basically the engine, and you probably don't want to know how it works on the inside, but it's good, I promise. The second thing is what we call strategies. So here we've imported hypothesis.strategies as st, which is pretty common, and we're saying that our argument is going to be one of a list of integers or floats, or a list of text strings. Does this basically make sense to people? Somewhat? Okay. And if we run this, what hypothesis will do is it will generate, by default 100, you can tune this, different arbitrary inputs and try to find one that makes your test fail. Is there such an input? Like, just looking at this test function, is there an input that would make this test fail? You're all very quiet. It's late in the day. Maybe you haven't had enough caffeine. It's okay. No one really wants to think about not a number, but it does exist. And hypothesis will remind you of this at every opportunity. And in this case, we've just said, okay, fine, not a number exists, but I'm not talking about that here. Like, only give me nice numbers. And so that's property-based testing. The basic idea is that it lets us describe what kind of input data we should have for our test function. And then it will generate specific cases that we might not have thought of by ourselves. Even if we don't know the right answer, we can often work out ways to check whether we're getting the wrong answer by checking different invariants of our code. And often I've found this actually helps me discover bugs in how I was thinking about the problem. Not just like typos in my code, but fundamentally wrong approaches when you start to uncover an edge case. And the other thing that I didn't show you in the slides was that often you don't actually need to put the assertions in the test function. Often you can put the assertions in the code that you're writing. And an assertion there basically says, this condition should never happen. Like, if this condition happens, it's because I have a bug somewhere. And that turns out to be really powerful because it means that the rest of your code can basically be assured that you don't have that kind of bug, that if that condition did hold, the assertion would fail and your program would crash. Don't rely on them for like important security things because you can run Python in a mode that doesn't check assertions, which is useful for performance reasons, actually. You can write your code with lots and lots of assertions that would be too expensive to run. There's a check just here. And then when you're running it at large scale, you can disable the assertions. Often, though, I actually just leave the assertions running because I think the small hit to runtime is totally worth it to be protected against bugs that make all of my analysis or work completely meaningless if I didn't notice them. Just a quick show of hands. Who here has written code? Keep them up if your code has never had a bug that affected your research. I'm so sorry. Me too. But we're going to try to do something about that together today. So this brings us to the end of the introduction to property-based testing section. Next up, we're going to grab the GitHub repo, pip install the requirements, and stand up a notebook. You can also try to click on Binder or open them in Colab if you prefer. And I'm going to take the next 15 minutes or so to try to make sure that everyone has this installed and ready to run after we talk through the next section. So let's go. If you get stuck on something, just raise a hand and I'll run around to help, or your neighbors might also be able to help. Yep, that is RSOKL/testing tutorial. Let me be a little more specific here. Where we say step 4, practice, specifically if we can open the second notebook. So like run Jupyter, get the second notebook loaded, and then I'm going to give the talk before we actually go through it. But like once you're there, you know we're ready to move to the next step.
Is there a 0, 0?
thank you. Let's jump in. Here is our beautiful logo named Scout. And let's talk about how to describe your data. So just a few slides ago, we saw this example of how to describe lists of stuff. Who here writes only functions that takes list of stuff? No one? Didn't think so. Array of stuff? Couple of people? Okay. Well, brief overview. This slide is a mess, so I'm just going to keep going. There's too much text. There are a bunch of different things you can generate, and the goal of Hypothesis is that anything which is a value you could represent in a Python program, you can conveniently get Hypothesis to make you an instance of it. So where do we start? We start with like very simple primitive element types. You can generate none, true, false, numbers of all kinds, strings, whether they're Unicode or byte strings, dates, times, time zones, timestamps, whatever else. There's a whole bunch of other stuff. You can look in the Hypothesis docs if you need it, or you can just use tab complete because editors are pretty good these days. We're going to do some like live games together. It's kind of like a game show and I'm the host. So let's try this test. Given any binary string, which we'll call S, is binary string S does not crash? Any guesses as to what happens when you run this code? Not anymore, because the authors of this library now use Hypothesis. But it did, in the old days, crash. So if you want to test something you don't need to assert, you just need to call it, especially if you've got assertions in the code that you're testing. Specifically, the thing that happened here was that it got a Unicode decode error on AEC5DC. And it's like, what the heck is going on here? There's a library called Chardet, which tries to detect what character encoding a given binary string is probably using. So if you have like an ASCII string or a Latin 1 string or like whatever other weird historical text encoding, it should be able to tell you what's going on. But as documented, when it says encoding, probability 100%, it doesn't actually imply that that's a valid encoding to decode the byte string. It just means that the prefix it looked at seemed valid. Personally, this is not how I would design an API, but the test here actually found a bug in the way we were understanding the code. Or more specifically, a bug in the understanding of the author of one of the libraries we were using with respect to one of the libraries that they were using. So this goes all the way down the stack. Like, is that a bug exactly? It's kind of unclear, but it's certainly something that I wanted a tester to find for me. Let's try this other one. Who here has heard of Mercurial? A couple of people. It's kind of like a Git alternative written in Python. It was very popular for a while. And so it has some utility functions from UTF-8 and to UTF-8b. And does anyone want to guess what happens if you take a binary string, convert it to UTF-8, and convert it back from UTF-8? And check that you got the same string? It doesn't? Something happens? Yeah, you guys have got me clocked. Incidentally, before I show you the answer, this kind of test, where you like round trip between two formats, where you save data and then load it back, where you convert it from format A to format B and then back to format A, this is a really powerful kind of test. Because when you parameterize that, like you're writing a test with quantifiers. You're saying like for all inputs, this should be true. And your data saving code, like basically everyone's code is going to load data and save data. If it doesn't, then you can replace it really, really quickly. There are some great performance optimizations for pure functions. But the other thing that these tend to do is they tend to cross many layers of abstraction. They're often dealing with operating systems or storage layers or protocols, different file formats, different languages, and it's really easy for somewhere in that deep stack of abstractions for a bug to creep in. And so this turned out to be just a genuine, very clear bug when they started using Hypothesis. They found a short byte string which couldn't be round-tripped. They fixed it.
Why couldn't it be round trip?
Unicode is cursed. It's like, this is not a place of honor. Nothing good is buried here. I know more about Unicode than anyone should. Like the distinction between a grapheme cluster and an extended grapheme cluster, which is different from a character or a glyph or a code point. in any case, let's talk about date times, which are a nice, sane, sensible thing. This one's pretty simple. It says we'll take our datetime object from the standard library, we'll get the ISO format string, which is nice and unambiguous, and then we will parse that formatted string, and then format it again and check that we got the same string. We should just be able to like parse the formatted and assert that we got the equal date time, but we're doing an extra step for whatever reason. This turned out to fail because it swapped the year and the month if and only if the year was before 10 AD and the number of years was equal to the number of seconds. I really can't blame the authors for this bug. This bug is ridiculous. Like, does it matter? I don't know. Would any other approach have caught this? Almost certainly not. So much for different elements, different atomic types we can generate. We can also generate collections of things. And there are basically three fundamental ways to do this with hypothesis. The first is the lists strategy. Then there are things like sets and dictionaries and frozen sets that are basically a thin wrapper around lists. So lists takes a strategy for the elements. So this is already recursive. Whatever you want to generate as the elements, you just pass it a strategy to generate that thing. And you can nest these however you like. You can give it a minimum and a maximum size, both of which are optional. You can give it unique by, which, if it's not none, can be a function or a tuple of functions. Or for convenience, you can just say unique equals true if you just want them to be unique and you don't need to specify what that means. A separate thing that you might want is tuples. So the tuples function takes n strategies and gives you tuples where each element is drawn from the corresponding strategy. So you could say, give me a tuple which consists of 3 integers and a string, and you would say tuples, integers, 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 text. Or there's fixed dictionaries. This basically is similar to tuples. You specify the keys and then the strategy corresponding to the value for each key. And you can have both required and optional keys there. So you can kind of see how you would start to build this up into more complex data types. So who here has done floating point arithmetic before? Yeah. So we say, given a non-empty list of floating point numbers, the minimum should be less than or equal to the mean, should be less than or equal to the maximum. Sound reasonable? Any guesses as to what will go wrong?
It's like the same number, but you have like a little epsilon issues. Maybe.
Yep. Maybe epsilon issues do something nasty to you. Any other guesses?
There's different nans.
There sure are different nans. Hopefully that doesn't make a difference to you. If you have a bug that only happens when your nan has the sign bit set, this will not be a good day. But Hypothesis comes with a custom pretty printer, so you'll at least know about it. The very simple version here is if they are large enough that adding them together gives you infinity, then your test will overflow, right? The mean will be infinity divided by 2, which is larger than the maximum or the minimum. You could also get underflow to 0. The other interesting thing here is that the list that Hypothesis reports to you is the simplest possible list, according to a pretty natural definition of simplicity. It's only got 2 elements, and this test can't fail for any single element list. I guess it could for a single element list containing nan, but as I said earlier, we're mostly ignoring nan. And it's picked 2 very sort of natural inputs for this. And so that's one of Hypothesis features. When it finds a counterexample, it tries to not just find you a counterexample, but a locally and usually globally minimal counterexample, which makes debugging a lot simpler. Once you've got your simple strategy, there are a couple of things you can do with it. One is that they have a map method. So you pass it a callable, it generates a thing, calls your callable on it, and then gives you the return value. So you can use this to construct instances of things. For example, if you want a sorted list, you can just make a list and then map sorted over it. And then there's filter. Filter, you pass it a callable, and it only gives you inputs for which that callable returns a truthy value. This is really useful if you want to reject like pretty rare inputs. Like if you're going, give me arithmetic expressions but not division by 0. It can be kind of annoying to work out how to construct a strategy such that it can never generate that in the first place, and much easier just to recognize the occasional instance and throw it out. This works much better than you would expect. We have a bunch of like smart adaptive stuff to try to make it efficient, even in cases where it shouldn't be. But if more than like 20 to maybe 50% of your examples get rejected by this, it's probably worth finding a more constructive, sort of higher performing approach. Because like, it does cost you a little runtime to generate an input, check it, and then throw it away. So if you want an ordered pair of numbers, this is like how you do it in the two styles. You start by going, give me tuples of 2 integers. And then you could say, like, filter this such that the first one is less than or equal to the second one. Or you could say, just sort them and then turn it back into a tuple from a list. And like, the latter will give you about, like, the first one will reject about half the samples, the second one will reject 0% of the samples but be slightly slower. So it's much more efficient overall. I'm basically just running through a big introduction here. There will be exercises where you can try some of this out in a minute. Sometimes you want a strategy that only ever produces a single value. Because we have an interface where you have to pass a strategy, for example, to lists or to something else. You're like, I know you need a strategy, but I just want it to be this value. That's what the just strategy is for. It just generates whatever the argument was. There's like no possible choices. It just gives you exactly that thing. And then sampled from is like a little more complicated than that. You give it the list of options or the sequence of options, and it randomly picks one of them for you. Sampled from also works well with nums, so like it can generate combinations of values and so on for you. And then you can combine strategies. So we saw this earlier where we had lists of integers, pipe operator or floats. One of is just like the function form of that. You can take the union of strategies, which just means pick one of these strategies and then generate a corresponding element from whichever strategy you picked. And to make that something nicer, like there's a strategy called nothing, which is just like the empty set. It can never generate anything, but it means that if you have an interface or like a helper function you've written that expects to take a strategy, like mix in a bunch of different possible cases based on the arguments, you can just return nothing if you don't want that to have any effect. Unfortunately, it is not possible in general to subtract strategies or take the intersection of them. Like they're conceptually sets, but the way they work is by actually executing code to generate a thing. And like trying to reason about the behavior of arbitrary user-supplied code to do set intersection is not my idea of a fun time. Who here has ever defined their own class? Most of us. Supposing that you want to get an instance of a class, you can use the builds strategy. It's pretty simple. You pass it the thing you want to call, and you pass it strategies as positional arguments and strategies as keyword arguments. We draw the elements from each of those strategies, and then we call your thing with them as positional and keyword arguments. So it's pretty straightforward. You could basically re-implement it like this, where you create a tuple of the positional args and a dictionary of the keyword args, and you like unpack it with map into calling the thing. Builds itself is actually a bit fancier than this, because it will do things like inspect the type annotations, and be like, oh, you have a required argument x, which is an integer. I know what integers are, let me get one of those for you. So generally, if you just say, like, build me one of these, it will work pretty well. Anyone done stuff with recursive data types? Things that can be nested inside themselves? There are a couple of ways to do this. One is the composite decorator, which I'll show in a moment. One is what we have on this slide, where you can just explicitly say, this is a recursive thing, it has a base case, and here is how you get a non-base case. So here we say that JSON is recursive. The base case is none, booleans, floats, or text, and the non-base case is lists of whatever that was, or dictionaries of string keys to whatever that was values. And so that can generate any possible JSON object. And then to save you time, Hypothesis goes to quite a lot of trouble to try to save you time and generally make life easier. There's the from type strategy. Who here uses type annotations or type hints? A couple of people? For those who do, you can just pass a type to from type, or in many other places we will do this automatically if you don't supply the argument. And this is explicitly designed to save you time, not replace other interfaces. So you can, for example, infer some arguments but pass something more specific for those where you have something more specific in mind. And then there's register type strategy, so that you can say like, okay, for this particular type that I defined, you should infer this particular strategy. Maybe some arguments have to be non-negative. Who's used regular expressions? Hypothesis can give you arbitrary strings that match an arbitrary regular expression. This is a particularly good trick because Python's regular expressions do not actually describe a regular grammar, which would have made it a lot easier if they did. Who here uses NumPy? Hypothesis can also generate arbitrary things from a NumPy data type. So if you have an array of whatever, including record arrays, including whatever cursed nested things you have, it all works. We also have a fun trick in the mutually broadcastable shapes. You can give it a array ufunc signature string, like for matrix multiplication, and it will give you broadcast compatible shape tuples to describe the arrays that should be valid inputs to that function, as well as the expected output shape. You can write your own functions that guess what strategies should be there, or infer it from some kind of schema or data description. This is a really useful pattern to save people's time. So a couple of tips. One is highly recommended to always err on the side of generating things where people are like, no, why did you feed me nan again? I don't want that. I don't want zero-dimensional arrays. I don't want whatever. Make people specify what inputs they don't want. Like, Hypothesis will do this to you. I'm kind of sorry that it's frustrating, but I think it's good for you. Because the alternative is that you have tests which look like they're testing something, but they silently decided not to check an edge case which actually mattered. And I think that's a much worse failure mode than having to spend a few minutes extra to specify the limits of what you wanted. And the other thing which Hypothesis tries hard to do, which I think really helps, is to make sure that there's a really smooth pathway where some magical interfaces kind of have the problem where they didn't do this, where it's like, if you're on the happy path, everything is auto-magical, it's super smooth, you just like say, do the thing, enter, and it works. And then you're like, okay, now I want to tweak one argument somewhere. And suddenly it turns out that you have to do everything by hand and start over. Hypothesis tries not to do that. We try to make sure that you can pass just the bit you want to customize, just where you want to customize it. That's usually more work for the implementer, but I think it's worth it. I will skip through this example. So everything we've described so far has really been like self-contained bits of data, where you sort of have a complete description of what it is and you build it up by composing parts. And that's most of the time, and it's beautiful when it works. But sometimes you have things that have like internal dependencies, like you want an array plus a valid index into the array. And you can't, in general, generate these independently, right? If you have variable size arrays and you have indices, then either you're only going to generate an index into the early part of the array that's like your minimum size, or you're sometimes going to have an out-of-bounds index. And if you don't want to filter, which is a valid time tactic often, there are a couple of ways you can do this. The one that you'll usually turn to is @composite. So this decorator wraps a function that you defined, and it injects a first argument to that function. By convention, we call it draw. And what draw does is it's a function that takes a strategy and gives you a value from that strategy. And you can then define other strategies based on that. So for example, you could pick the array size, then generate an array, then based on the array size that you generated, pick an index into the array. Or in this case, we have a bunch of arguments to it. We pick a factory location, we pick a power rating, we then generate a widget which was compatible with that. Examples are hard, like naming things. There's also a flat map method, like the map method. Map takes a value and returns a value. flat map, you supply a callable which takes a value and returns a strategy, and then the method draws a value from the strategy that you returned. So it's equivalent to composite. It is mostly useful for people who like cute functional programming tricks, but if that's you, we have it. And then this trick, I call it like the inner composite pattern. And what this lets you do is you define an outer function which takes all of your arguments. You do whatever input validation you want to do. You do whatever processing of the arguments you want to do. And then you define just sort of the smallest possible composite wrapped function with no validation inside it. And that means that you amortize the cost of all your validation, so you only run that once instead of each time you go to generate a new value. Of course, in many cases, you can just define a function that returns a strategy. I really like it when people just define functions. I think often it's easy in Python or in programming or when you're doing fancy stuff with hypothesis to get caught up in all the cool interfaces you can use and the incredible power of functional design patterns or whatever else. And sometimes you can just define a function that returns a value. And this is a good pattern, right? I like functions, they're useful. You often don't need more than that. Okay. And then I think this is close to the last thing I'm going to tell you about before we get to exercises. Data is like the composite decorator, except it lets you draw from strategies inside your test function. And so this is like the ultimate power. You can interleave data generation and executing the code that you're testing however you like. The downside is it's harder to report what the failing examples are, so the user experience is not quite so polished. The upside is you can have just arbitrary dependencies. And so you can run your simulation for a bit, look at the current state, pick an action based on that, and then keep going, for example. Use it if you need it. Try to avoid it if you don't need it. I'm getting into cliches, I guess. All of the strategies I've talked about so far are actually built into Hypothesis itself. So the core strategies have no dependencies outside the standard library, and they're found in the hypothesis.strategies module. In other programming languages, these objects are called generators, but Python already had a thing called a generator, and so we couldn't name it that. We've had off-by-one errors. Turns out naming things is hard. Those are two of the hard problems in computer science. We also have extra strategies, like hypothesis.extra.numpy. Do you want to guess what that one generates? That would be hypothesis.extra.pandas for pandas strategies. The NumPy extra generates NumPy things. We also have .arrays for arbitrary array API compatible libraries and a whole bunch of other stuff in there. And there's even more stuff that is not shipped as part of the hypothesis package itself, but on PyPI as third-party extensions. There's a list in our documentation. We don't endorse everything on there, we just list them. Okay. We now get to the fun exercises portion of the day. Now that we have gone through installing Python packages, which is always a great start to a session, we're going to go with the Notebook 01, Describing Data, which aims to get you hands-on experience generating different things using the Hypothesis API that I've been talking about. Combine them however you like. We'll probably spend 20 to 30 minutes on this. I'll sort of keep wandering around offering help with people. Feel free to stand up, take stickers, share stickers, go get a drink, whatever else you want to do. And then when we've wrapped up, I will call everyone back and we'll go into the third and then fourth section of the talk. All right. I think I owe you a brief correction to some of the tutorials material. At one point, we have an example where we demonstrate a filter of 10 less than or equal to x less than or equal to 20, and it's documented as this should give you a health check error. However, I got overly clever recently and actually made hypothesis, get the source code of the lambda and get the abstract syntax tree of the expression of the lambda and extract the constants and rewrite the strategy, which I swear made sense in context, but also meant that this example now works when it was meant to not work. If you have the bounds defined as variables, so you say like low equals 10, high equals 20, and then compare x to low and high, it will give you the expected health check error. And I'm sorry for not noticing this in advance.
I managed to come up with an example that gives that error.
Nice.
I filter the integers by asking for them to be greater than 1 billion. And sometimes it takes a couple tries for it to actually get the error. But I tried 28 that seemed to pass. It turns out to 29.
Nice. right. I've been wandering around and people seem to have been making great progress through the describing our data section. For the sake of time, I want to skip us on to a couple of further parts. So this is going to be section 3 and section 4. We have exercises, of course, like the things are on your laptops, the things are on the internet. You can keep working through them throughout the conference. Come find me or do it later as well. Okay. Who here gets sick of writing test code sometimes? Me too. That's not why I wrote the ghostwriter. The ghostwriter is old-fashioned AI, by which I mean that while I work at an AI startup, the ghostwriter is implemented with if statements, dictionaries, regular expressions, string templates, and a bunch of careful data analysis to write big tables of what you should do in different situations. And I am going to try to give you a live demo. And I've found that live demos work better when they're interactive, when the audience kind of gets in on it. So every time I say the words live demo, I want all of you to say, what could possibly go wrong? Are we ready? I'm going to do a live demo. Thank you. Well, let's find out, shall we? Okay, so can people see this? I'm going to zoom in a bit. Hopefully that works. This is kind of a low-resolution projector. Hypothesis, by default, installs a command line interface. It has a couple of commands. You can do code mods, so that when you update Hypothesis, it will automatically upgrade your code for the new version whenever possible. We can fuzz test, which we'll cover later, and then the write command is maybe the most interesting one. What do we run a test for? How about gzip? If I can spell gzip. So this is a compression module, and let's put it in test.py.
So when you write gzip.compress, it looks for a Python library?
Exactly.
I guess compress is a function within gzip.
Yeah, so gzip is a standard library module which has a compress function which takes a byte string and opens some other stuff.
I read hypothesis right numpy.
Oh, that's a great question. Sorry, let me close a bunch of these. So this is, if I close all of my other tabs, sorry about this. Yeah, it's fine. I wasn't using that stuff anyway. Zoom in again. So hypothesis write gzip.compress has written us a test function. And in this case, it has observed that as well as there being gzip.compress, there is also gzip.decompress. It noticed this by the power of AI, by which I mean it has a table of try substituting the string of the function name in the following ways and check whether that exists. And in this case, you have a function x and you have a function dx. You might have also had unx, that works as well.
How would it decide if it sees both?
It just takes whatever one was first in the list of things to check. Like I said, it's a little old-fashioned AI. But it's fast, it's local, it's nice and private. And in that case, we've assumed that because we have an x and a dx function, we should be able to round trip them. That is, if we compress a thing, then it seems reasonable to call the decompress on whatever the output was and check that we got the input back. So let's try running this. Oh, good grief. This has gone in silly places. Anyway, I appear to have balked my environment a little. Let's just... Yeah, thank you. That's what happens in live demos. Thank you. Okay, let's try this live demo again. There we are. Okay. So we have test.py, and any moment here we have our test code. That's excellent. So now if we run pytest test.py, we are going to get some output, and the particular output that we get is just going to say, this failed because you can't generate data from the empty strategy, data equals nothing. And indeed, that's why we have the to-do comment. So what we actually want is a binary string. And if we replace that, and then we run pytest again, this test will now pass. So the ghostwriter is not guaranteed to give you working test code. What it's designed to do is get you past the blank page problem, so that you're looking at something which is clearly calling your code, and you can sort of go, no, that's wrong, or, oh, that's missing something. It'll leave to-do comments where it can, it'll use type annotations where it can. It will, in some cases, guess based on variable names from which I did some data analysis. And the idea here is to show you ways that your test code might work. Yep?
Can you elaborate on specifically the it'll leave to-do comments again? Like
So where it had a data equals nothing,
yeah.
this is because it had a variable, or like an argument to your function, with no type annotation, and a name which is not one of the shortlisted things that we know how to generate. So it's like, well, I will put in a placeholder, so the test will fail, and the user will have to substitute in what they actually meant.
Is it pretty good about putting in proper, like, not doing nothing if you your code well?
Yes.
Okay.
Someone asked about NumPy. That does indeed work pretty well. So here's the test for NumPy matrix multiplication. We will get mutually broadcastable shapes according to the following broadcast signature, plus optional leading dimensions which are broadcast compatible. It will use whatever data types the ufunc declares that it supports, and then it will generate a bunch of stuff, call it, and check that we got the expected shape and dtype of the output. Yep.
So I was trying to use ghostwriter last week, and it didn't create the test file that I wanted, but it just created an empty file. You know what's going on?
So you tried it last week, it just created an empty file. My best guess is that it was just still thinking, if it was a large library. You might have noticed early on, like when you pipe into a file, the file gets created, and then when the command has output, the output gets piped into the file. So my guess is, like, if you just do hypothesis write NumPy, there is a lot of NumPy, and it takes a little longer to write tests for all of it. There's no fancy multi-threading in this because I don't hate my life that much. There's fancy concurrency in other places. Okay, so that's the ghostwriter. The thing that actually inspired me to write the ghostwriter was 5 years ago when I went to PyCon for the first time. And I was talking to people, I had like hypothesis stickers on my badge, and they often said things like, oh, hypothesis seems really cool, but I haven't used it on my code. I'm just not sure how to get started or where to apply it. And so like, one of my solutions is to run tutorials like this one. Hi, everyone. Thanks for coming. But the other solution was to try to do that classic programmer thing of going, I wonder if this social problem has a technical solution. I can like write some code and get out of talking to people that way. And so the ghostwriter, I think, has actually been really successful at getting people engaged, getting people to actually try using hypothesis. I think it is also genuinely a bit of a time saver for people who are already using hypothesis, but the main case for it was actually to convince people to try using my library literally at all. So let's get into part 3 where we talk about common test tactics. We'll have seen a bunch of these. And the idea of this section is I want to tell you about categories of tests that you can probably write for a wide variety of your code, including hopefully some of your code. So we'll go through common properties, a couple of situational ones, and then we already just talked about the ghostwriter. The ghostwriter basically uses those if statements and regex that I mentioned to try to encode some of these common properties in a way that we can automatically recognize. It works shockingly, embarrassingly well to just call your code, not have any assertions in the test, not really check anything about it, just that it doesn't crash. This does two things. The first is it encourages you to explore how to generate every possible edge case of the data that might be fed in. I find this actually often changes the design. It makes me think more clearly about what data is valid. Often I end up like writing the first part of a test and then like thinking for 5 seconds and then going and fixing my code before I run the test. But even aside from that very real benefit, just calling your code with any valid input will often find crashes, and it will prepare you to write more complicated tests because you've just worked out how to generate any valid input. So it feels embarrassingly simple, but don't neglect this. The other one that we've seen, in the gzip example, is round trips. I showed some of these on the slides earlier as well. Save something and load it back, encode it, decode it, send it, receive it, convert it between data formats, multiply and divide. Whatever it is, these round trips, like every code base has round trips. Any code base that does not load data and does not save data can be optimized enormously by deleting it. Right? No input, no output, no code necessary. But where you do have save and load, these can be really powerful properties and also very easy to write once you've worked out how to generate your inputs. So once you've called your code, checking that you can load and save data and get the same data is really, really powerful. This is literally where I recommend people start. Like the first test you write should be the just call it. The second should be try to save something and then read it back. Another really powerful set of property tests is like equivalent functions, single thread versus multi-thread, the old version, the new version, calling functions in different orders when they should be commutative. And sometimes you can do this on like a subset of possible inputs. So for example, you might say like, my function is valid to call on all numbers, but if all of the inputs are positive, then there's this additional property I can check, that it should be equivalent to this more specialized thing. This is more situational, but when it's available, it's really, really powerful. And it's not terribly uncommon to find yourself implementing something in Python, which also exists in some other library or software ecosystem. And that can give you a great source of these equivalence tests where you can say like, well, I'm trying to port a thing from MATLAB, for example. Let me just like run the two scripts on various inputs and check that they get the same answer. And hypothesis, importantly, will give you a minimal input which gets different results if there is one, which is often a lot easier to debug. And who knows, you might decide that the old code has the bug, not the new code. But that's worth knowing too. Just validating the output always feels really silly to me. Probabilities should be between 0 and 1. The type should be an integer or a float or an array or whatever it is. The thing should not be empty. These do catch bugs. I always like to write them as assertions in my code rather than my tests. Because if these conditions come up during production or during a research run rather than during a test run, I still want to know about that. I think about this as like finding out more quickly when I've written a bug in future. Property-based testing is named by people who liked functional programming. So they were naming them for things like properties of algebras over the reals. So, if your functions happen to be idempotent, commutative, associative, whatever else, like just check your algebraic properties as well. They're pretty rare in Python code, but if you have them, they're easy to test, and just to show off, the Ghostwriter will do that for you too. Who here deals with like simulations of some kind on a regular basis? A couple of people? Hypothesis has a module for what we call stateful testing. I'm not really covering it in the tutorial, I'm just going to tell you it exists. The idea here is that you define a class with various methods that are like actions you can take, maybe with preconditions, and then a hypothesis will choose a sequence of method calls as well as the arguments to each of them. This kind of defines a state machine. It's really powerful for exploring different interfaces. But all I'm saying here is they exist, they're pretty useful, you might want to check them out later. The kinds of properties you can write get much more complex as well. The sort of last complicated general category I'm going to talk about are what are called metamorphic relations. I'm specifically talking about these because they in fact come up all the time in sciences in particular. The idea is that while we might not know the exact relationship between an input and an output, we do know that if we have two inputs with a known relationship, then the two corresponding outputs should also have a similar relationship. For example, maybe something is scale invariant. You don't know what the function is, you just know that it's scale invariant. So you can generate an input, pick a small scale factor, run the code on both, and check that the outputs are related by the same scale factor. Make sense? Maybe you double the amount of energy, or you run for longer, or whatever it is. In compiler testing, this is often used to make arbitrary modifications to unexecuted code, and this shouldn't affect the result when you compile the two versions and run them on the same input again, but compiler optimizations mean that maybe it did. Or if you negate things and then sort them, this should give you the same as sorting them, then reversing the list, then negating them. But my basic rule of thumb here, having just told you about the complicated thing, put assertions in your code, then just call your code to see if it crashes, which I'm calling fuzzing, then write some round-trip tests, and you are basically done. It should be very obvious to you then, if you feel you've still got more value to get from property-based testing, you're probably right. If you don't, you'll have already gotten most of the value out of it. There are many projects which have like 1 or 2 or maybe 3 property-based tests, and that's enough for them. There are others where most, though almost never all of their tests are property-based. So having said you can then relax, we're actually going to do some more exercises. We are now up to the O2 notebook, which will cover different common categories of tests you can write. And we're going to spend, let me look at the time, we're probably going to spend about 40 minutes on this one. So if you want to take a break, now's a good time, or if you want to jump in, I'll be circulating again. Hey everyone, it's been brought to my attention that there are snacks outside. So I don't know about you, but I'm going to go get some snacks. And I'm going to aim to start the fourth and final section of the talk at about 10 to 4. So that should still leave us plenty of time for talk and questions, but back here at 10 to 4. Until then, snacks. Or tutorial, your call. All right. So we've had some time to work through the exercises on common categories of tests and hopefully to get some snacks and restore your blood sugar. So I want to give the fourth and last talk section of the tutorial, which is about putting it into practice, kind of practicalities, configuration, other things that you'll want to know when you go to apply this to your own projects. And then the remainder of our time, like I'll be here until 5:30. Very happy for people to continue working through any of the exercises. There's a few about this, or we can go back to the data description or the test categories exercises as well. So, most of what I've covered so far has been the kind of core principles. I think like the most important bits for you are the confidence to actually just try using hypothesis on your own code, the ability to describe whatever kinds of data is valid or should be valid inputs to your code, and then having some idea about what kind of invariants or properties you might test. However, there's a bunch of other stuff that is useful, like what the heck do I do with this? No, really, how do I configure it? Do timeouts work? Is it deterministic? Like, will things be flaky? And that's what this question is aiming to do. So I'm going to run through a bunch of slides, and then I also want to do like an open Q&A. For the sake of the microphone, I'll repeat questions, but like shout them from the audience when they come up at that point. Okay, so the first thing I want to emphasize is that I think hypothesis is pretty cool, and I hope some of you do as well. But it is not a panacea. Not every test should use hypothesis. Almost every test suite should have a large chunk which does not use hypothesis. I think most test suites should also have a large chunk which does use hypothesis, and so here's the tutorial. Depending on the project, I've seen like typically like 10% to 90% of the tests being property-based. Sometimes like the payoff just isn't there. You like go to all this trouble to define your data and you'll be like, well, turns out there's 3 inputs and I could have just parameterized it and it would have been faster. Or actually, this script is a bit of a hack job, so I just want to have some snapshot tests where I have the known input, the known output, and I'll just check whether that changed. And maybe that's all the testing I need. The idea of hypothesis is I want it to be as easy as possible to reach for more rigorous testing when that's the right choice. So, write some property-based tests, write some that are not property-based. And then the other design pattern for a test suite, I think, is how do you manage the strategies for your project? Custom strategies are great as a source of truth for what are the weird edge cases that every part of my library needs to handle. Lots of those are built in. For example, hypothesis will tell you about not a number all of the time. I'm sorry, the IEEE made us. And by separating the definition of the strategies from the definition of your tests, you can update them independently. And this means that when you improve the strategies, every single one of your tests becomes more powerful. There are a couple of ways to do this. One of my favorites is to define some functions, like in a testing submodule, which return strategies for your objects. A couple of people have asked about Xarray today. Like the Xarray authors now ship some hypothesis test strategies in xarray.testing. So if you're using a recent version of Xarray, the library already knows how to describe how to generate its own objects to hypothesis. A somewhat simpler thing is just define some globals, like literally write strategy for whatever equals st.whatever. This works great. It still saves a huge amount of time when you need to customize that or tune it a little. You don't have to go grepping through your entire code base to find every place you use that because you just imported the one instance. And then finally, there's the register type strategy function for custom types. Maybe you have something where you have type annotations or not, and you can specify exactly what should a default instance of this class be so that everywhere else hypothesis will infer just that for you. Any questions on this? Some head shakes? Let's keep going. Who here has written print during this tutorial? You would have noticed that it gives you like a wall of output. And that's useful when you want a sense of everything that your test is doing. But sometimes you want something which is like print, but only for the minimal failing example. Hypothesis.note is exactly that function. It does exactly the same thing as print, but it only actually outputs to your terminal on the last minimal failing example. So this means that you can do print debugging without scrolling past a wall of like hundreds and hundreds of redundant things. And the other useful function here is event. Event actually summarizes across multiple input examples. You give it a string, and if you pass the statistics argument, hypothesis will tell you what fraction of your runs had that event happen. And so this can be useful if you want to know, like, how balanced am I between different scenarios in this test? You know, is it working as I expect, or am I almost never doing a particular class of thing? The statistics output looks, something like this. You have a test, and it will tell you during the generate phase, here's what we did. During the shrink phase, here's what we did, and then we stopped because we were done. So in this case, we have some runtime information, how many passing and failing examples. It was 40% this, 60% that, and so on. People have also asked about settings. I'm not going to go through every single setting that Hypothesis offers. You can find those in our documentation. But there are a couple of things to know. We have this concept of settings profiles. So you can, for example, have the settings for local development and the settings for CI, and just address those by name. These are all set from Python code. So if you're using PyTest, that would usually go in conftest.py. We do not support loading them from environment variables, from config files, from anything else. It's Python code. You can all work out how to do that from Python code if you want to. Like, you want to load it from an environment variable, os.environ.get, whatever, write an if statement. You can do it. I believe in you. You can also apply @settings as yet another decorator because Hypothesis loves decorators. And that will affect just that particular test. So if you have just written a single test and you want to check something, you can apply @settings max examples equals 1 million and just run it for an hour to be sure. And then we have a PyTest plugin so you can select the profile and certain common settings on the command line as well if you're using PyTest. Questions here? Okay, the performance-related settings. Who wants things to go fast? Who wants things to be rigorous? We like both, but there's a bit of a trade-off where the more rigorous you are, the longer it takes. So you get two common settings for this. One is a deadline setting. This is how long does each test input have to run before we tell you that it's kind of oddly slow. By default, that's 200 milliseconds. If you're doing things with large arrays, you'll probably want to turn that up. In CI, sometimes, like, performance on virtual machines can be kind of randomly variable. You might just want to set deadline equals none to disable this. That's totally fine. The whole point is just to warn you if it's unexpectedly slow. If it's expectedly slow, that's fine. The other is max examples. Max examples is the number of passing inputs that Hypothesis will see run to completion before it decides to stop looking for a failing input. So if you use filter, that will not count towards this number. If you have an assume or a reject inside the body of your test function, which is just like filter, likewise, that will count as an invalid input and will not be counted towards this quota. Obviously, if you turn it down to 1, it will be about 100 times faster, but also less rigorous. If you turn it up to 1 million, it will be about 10,000 times slower and somewhat less than 10,000 times more rigorous. So make your own judgment here. It depends a little on the size of your search space. I generally don't even touch this setting though. I just leave it alone and it's fine. If you really like deterministic things, we have a de-randomize flag, which makes things exactly bit for bit reproducible. You can also specify hypothesis seed on the command line. If you do this, I strongly recommend running non-deterministic tests in a different CI run, or nightly, for example. The reason you might want to do this is that some people want their tests in CI to only check whether the pull request introduced a new bug. And if you have it running non-deterministically, then it can also find pre-existing bugs, which sort of then blocks that pull request on fixing this pre-existing thing. It is, I think, basically an aesthetic or workflow preference, which of these you prefer. Hypothesis by default is just trying to find bugs for you. But if you prefer the de-randomized one, you can do that. And then you can run like a longer overnight test run non-deterministically to see if you just missed a bug in CI the first time. A friend of mine wrote a good blog post on this, nullpage.com, subtitled 2 Kinds of Testing. Who here uses random number generators? Who here loves flaky tests? No one. Well, good news for you if you're in exactly one of those categories and don't love flaky tests. Hypothesis has a bunch of good support for random number generators. One is we have a randoms strategy, which will give you instances of random.random. You know, if you want your code to be deterministic, you can literally pass an instance of random, and then there is no global state, and everything will be good. And no one actually does this. So Hypothesis will also seed the global random number generator before and reset it after every single test. We do that for the standard library. We also do it for NumPy. And you can also, via things I will not describe now, register a random number generator in some other library so that it gets handled the same way. That all works pretty well. If you then want to vary those random seeds, the random module strategy will do that for you. And if something is weird, just like open a GitHub issue and I'll probably fix it for you. Reproducing failures. I didn't see anyone who loved flaky tests. So there are a couple of ways to do this. One is you can just literally rerun the same test, and Hypothesis will transparently cache the choices that Hypothesis made to generate the failing example and try replaying those each time you rerun that test. So if you just run your test and it passes, then run your test and it fails, and then run your test again, you can be confident that it will fail again rather than passing again. However, if you're sharing this across multiple machines, multiple developers, whatever else, I would encourage you to add this at example decorator. Quick show of hands, who actually worked through that part of the tutorial already? One person? 3 people? Okay, a couple more. The tutorial material shows this off. At example is just like at given, except instead of taking strategies, it takes the values that could be generated. So here we have some example domains, and then at given with the domains strategy. For use in CI, where things are cursed and wrappers don't always make sense, we also have this print blob setting, which defaults true in CI, based on the environment variables we observe. It will give you an at reproduce failure decorator, which basically just puts part of that database in line in your code. So this is like an ugly temporary thing, but it's really useful to get something to replay so that you can reproduce whatever happened in CI locally. If you're feeling fancier, you can also set up things such that you share the database between your local development and the CI environment. You can use whatever cloud data store or database for this. I will just refer you to the documentation if you want to look into that. Most people don't bother. If you do, I did in fact have this slide, you can just share it between, by default it's just in a local hidden directory. You can also put it in Redis. You can upload it to GitHub Artifacts and transparently download it. There's a lot of options. Any questions so far? Sorry, before I move on. Still no. Did anyone get coffee when we had our snack break? No. Oh no. Okay, well, I'll try to be quick. By default, again, there's a lot of times I'm saying by default because Hypothesis is quite configurable and has a number of other backends, but we try to make the defaults sensible. So by default, Hypothesis will mostly just be randomly exploring the space. We have some heuristics, for example, 0, plus and minus 1, infinity, powers of 2. These are all sort of interesting things, and so Hypothesis will try them more often than uniformly randomly sampling would. But it's mostly a sort of black box, throw stuff in, see if it crashes approach. Hypothesis.target gives you the ability to do a sort of hill climbing search. So this is not full-on gradient descent because we don't in general have gradients, but you can give it a score and it will try variations on things that scored highly for whatever labels. And so if you can come up with some kind of distance to bug metric, you can try to make Hypothesis minimize the distance to bugs. This turns out to be hilariously effective because guiding a search is much, much, much more powerful than just randomly guessing in huge, huge state spaces. You can, for example, if you're asserting that your result is close to the expected result, you can try to maximize the difference between them. This works really well to find cursed floating point things. You can try to maximize things like the number of tasks in a queue, the runtime of a particular function, like compression ratio. There's lots of fun stuff there. You can do coverage-guided fuzzing, where you, it's a little more complicated, but you basically have a genetic algorithm that is trying to find inputs that make your code do things that it hasn't seen before. Very powerful. Again, somewhat more annoying to configure. So Hypothesis is set up to be as easy to use as possible, and then if you later want to invest, gives you these more powerful, more fiddly options as well. I'm particularly fond of coverage-guided fuzzing via HypoFuzz, which is another library I maintain. It builds on top of Hypothesis and is basically designed for the run overnight kind of workflow. So it uses PyTest to find everything and then runs them in a really well-integrated way. Who here updates their libraries regularly that they're using? Who here pins all of their transitive dependencies? A few of you have good habits. I would recommend it to the rest of you. For those who do pin things, when to update Hypothesis is a reasonable question. We have a neat trick where every single pull request becomes a new release of Hypothesis. So I think the current version number is something like 6.105.8. They're well tested. We do take stability very seriously. Would you believe Hypothesis is tested with cutting-edge property-based testing library? But we do still recommend pinning your transitive dependencies because other people might not be so careful. So that is the fourth section of my talk on some of the practical stuff that you'll want to know putting it into practice. But it's not everything that I think you all want to know. So I'm now open for questions for as long as you have questions, and we'll then go back to the exercises for the last time that we have together.
Is there a way to make it so that if I have something testing, my test is long, like 100 milliseconds or something. Most cases it finishes fine, but fails, it tries all the possible other cases, and then it goes for a really long time. Is it possible to add a setting or something where, like, if it fails at all, it prints something unseen or something? I don't know. I'm trying to figure out how to. Sometimes my colleagues run my tests and they're like, why is it taking so long?
Yeah, so for the microphone, this is, suppose you have a slow test and it fails. Can you get something printed immediately or otherwise work out what's going on before Hypothesis takes a long time to find the minimal failing example? We do support disabling the shrinking to a minimal failing example. So you can specify which phases of the test run you want, whether it's only explicit examples, replaying them, generating them, shrinking them, or a couple of other bits. The cost there is that you don't get minimal failing examples, which I think are generally really nice. You can turn up the verbosity so that it prints every input that it's trying, and then whether it passed or failed. But I don't think we currently have a good way to immediately print, hey, we failed with this non-minimal input, and then shrink it anyway. You could implement this with like a decorator that goes between your test function and @given, so that the first time it raises an exception, you print whatever the arguments were and then pass them through.
Is the shrinking controlled in settings?
Is the shrinking controlled by settings? Whether or not to shrink is controlled by the settings via this phases setting, but the mechanism of shrinking is totally automatic and has no user controllable knobs.
Kind of related to that, is there like a sort of a rough guideline on how many times it will try to fail before it finds a minimal failing example, or does it vary a lot by measure?
Yeah. How long will it take to shrink in terms of the number of inputs? It really depends on the kind of data you're generating and how complex the initial first failure that it found was. If, for example, you are testing with Boolean arguments and it finds a failure, that will shrink very, very quickly because either it was false, in which case we are done, or it was true, in which case it will try false, and then we are done. So you get like maximum 3 test executions from that test. Otherwise, like, I can't say much more than it depends, but typically it would be in the hundreds to low thousands of executions total. So the default is 100 executions, then the test is passed. So it will often take longer if it fails, but not usually very much longer. We also have like a hard-coded, monkey-patchable 5-minute timeout. So if we're still shrinking after that long, we will just give up in disgust and show you however far we got. And if you then run the test again, we will replay that cached failure and continue shrinking. What's up with the logo? Great question. Some years ago, we thought, well, every project needs a logo. We picked a dragonfly because dragonflies are insectivores. They literally eat bugs. And we thought about a number of things that eat bugs as logos. Spiders are a classic example, but especially in Australia, not everyone wants a picture of a spider on their laptop. And I think this is pretty reasonable, really. Other things, birds, small mammals and so on, they're often photogenic, but they're less distinctive. Like cute, but a little different. And so we settled on a dragonfly because dragonflies are active predators. They actually go hunt down bugs, not just wait for them to come to the dragonfly. And they have one of the highest success rates per hunt of any predator in the animal kingdom. And so this convinced us to consider a dragonfly logo. Then a friend of mine drew this and we thought, okay, it looks beautiful. Originally it was all blue, just sort of beautiful monochrome shades. And then we thought, well, every logo also needs a pride variant. And then we drew the pride variant and we're like, well, we don't really need the blue variant. So this is Scout, the proud dragonfly logo.
Maybe it's just halfway to hypothesis or testing in general, which I think we do often in science. Anything with simulation or statistics, I think these tests are usually prone to, be not deterministic by design. Do you have any ideas of what's the best approach here? You already meant splitting things, but what are things that you would recommend, especially with hypothesis, to do that if I have, for example, I want a sample from distribution and I want to just see is that actually unbiased or anything like that that really takes a lot of time.
Yeah. How do you use hypothesis on things like simulations, which are by design non-deterministic? I think my answer there is sometimes this means you have a test for which hypothesis is not the right tool. But I would often think about this as use hypothesis to set up the broader parameters, like what's the shape of the inputs, the shape of various arrays. But then if you ask hypothesis for, notionally uniform random numbers, hypothesis will not actually give you uniformly random numbers. Hypothesis has all these heuristics. It will try to be evil. It will induce correlations. It will do all kinds of nasty things to try to make your code fail. So I would usually just say okay, hypothesis, give me the integer seed for the random number generator that I'm using. And then I'll generate some genuine pseudo-random numbers for this. For things which are just more generically non-deterministic, if you have a simulation that uses random numbers internally, again, you can just seed that random number generator with hypothesis, and you'll at least get the reproducibility, the shrinking, even though you also have randomness involved.
So I write scientific software that sometimes has very strong mathematical constraints on the input. So for instance, I need permutation matrices. So they have to be square, they have to have unity traits, and they have to be their own, they have to be equal to the conjugate transpose. How do I define that strategy?
How do I define things with really strong mathematical constraints, like must be a Hermitian matrix in a performant way? Man, if your mathematical constraints do not give you constructible objects, you are going to have a bad time. If they are constructible, then you can just run the construction. So take some random matrix, do a bunch of operations to it such that you get the matrix that you want out the other side, and then use that. This is a case, though, where you start to be like, wow, I really need some domain expertise to work out how to use hypothesis for this problem.
This may also fall in that latter case, but let's say I'll just use my domain, which is biotech, as an example. So let's say I wanted to create a strategy for just a region of the genome or something like that, right? And we know a priori literature that, okay, these regions are super sketchy and they have weird stuff So I assume we can use a strategy to like build certain objects. Let's say we have our own like fundamental data types, right? We can build that. That's fine. But then can we like make our own heuristics, or are we only stuck with the hypothesis heuristics, which might be like trying to put in infinity and stuff like that, which aren't edge cases for us? I would, like, as opposed to like domain edge cases,
Yep.
right?
So this question again for the microphone. Suppose you're doing something like biology or bioinformatics, and you're defining your own strategies for that domain. Can you define your own heuristics for what the weird edge cases are? Or are you just relying on hypothesis? The answer there is a bit of both. So you could describe a strategy which is, for example, any possible string of DNA, like generated with a text strategy or whatever else, or like one of the following known weird segments, and like generate a bunch of these and concatenate them. So you can do things like that to upweight particular edge cases. You can also just say like, well, I know hypothesis is going to try the start and end of integer ranges, and like, well, if I'm doing my thing, that turns out to just like flow through in a way that composes nicely. I think it's usually a mixture of these, where it's worth sort of thinking carefully about what are the weird edge cases that you do want to make sure are tested much more often than by chance, and sort of mixing those in with the broad distribution that covers most of the volume of your space. Well, if we are out of questions, I'm just going to, yep.
In the past, I've had a hard time getting this play nice with instance. I haven't tried this recently. Is that like still a thing?
Does hypothesis play nicely with PyTest XDist? In my experience, it seems fine. If you have a particular reproducing case where it doesn't, let me know and I'll be happy to look into it. In lieu of any further questions, I'm just going to tell you about a cool thing. So I've talked about random generation and also coverage-guided sort of evolutionary search techniques. The last thing that you might imagine we try is just ask the computer to reason about what this code does and find a failing example that way. This turns out to be an unbelievable pain in the backside, but we mostly have it working. So Hypothesis now has a concept of backends, and so you can have the default backend, you can have a SAT solver backed backend that uses reasoning, you can have a coverage guided backend, whatever else. And while we are still ironing out a bunch of bugs, we can now just say like, well, we have simply reduced the problem of finding a bad input to this well-known NP complete problem, which we can solve in practice. So if you only have native Python code with no compiled extensions, and you don't use a bunch of interfaces that we haven't implemented yet, it works today. Otherwise, check back next year. I'm pretty excited about that just because I've been working on it lately. Overall, though, I think that's all of the me standing up here talking to you. We have the room until 5:30, so I'll still be around to help people out if you want to keep working through the tutorial exercises or talk to me in a smaller setting. Otherwise, I just want to say thanks so much for coming, and I hope that you enjoy using Hypothesis and that it really helps you write reliable, enjoyable, productive code.